Hey everybody, hopefully you can all hear me. It's 2 o'clock, so we'll get started here. I am recording this, so if you need to duck out and catch the recording later, that's fine. I'm also going to post the Jeopardies on Moodle as well later. So I'm going to go ahead and start sharing my screen so you guys can see the Jeopardies. Hopefully everybody can hear me. If not, let me know somehow. Wave your hand or something. Okay, so I've never done this on Zoom, but I'm just going to follow the format that I used to do in class when I did these review sessions. We are going to go through Jeopardies, but the Jeopardies are going to follow roughly in the same order as the review. So if you have your review sheet or if you want to take notes, we're going to try to answer all the questions on the review sheet and get all these definitions. So you can follow along there, and occasionally I'll check back to this review sheet just so we know that we're covering everything. If you need to find the review sheet, it's on Moodle. It's under the Test 1 review sheet and homework information. And that's also where I'm going to post these Jeopardies after we're done here. Let me get rid of myself so I can see the Jeopardies. Where am I? Put me on there. I'll just make it small. Okay. So that you guys can see everything. So I'll post these so you can go back and review. We're just going to start with the first category and kind of go in order. That way you can get a sense of things. I usually write my test in orders too. So if you want to study that way, if that helps, that's what I do. Okay, so here we go. The study of what's in the universe and what it is and how it works. So it's hard for me to ask you if you guys have answers. So I'm just going to go ahead and give the answers. It's a new world, isn't it? So this is just a definition of astronomy, study of what's in the universe, what it is, and how it works. All things we observe in the universe are either blank or blank. So as you're doing this at home, I'm going to pause briefly so that you can think about the answer and try to answer it as you go. So all things we observe in the universe are either matter or energy or light. We in astronomy consider energy and light to be basically the same thing. So we have matter and energy in the universe. I just realized that it's hard for me with this to know if anybody wants to ask a question. So I wish there was a way. I don't want to show the grid. I can show this small thing. If I'll leave this as a thumbnail so I can see. If you have a question, go ahead and turn on your mic or turn on your video. I can't see everybody, but if you turn on your mic and talk, then I'll hear you, okay? So moving on. The part of the universe we live in that is bigger than the solar system, but smaller than the local group. This is a, sorry, lost my train of thought. This is a cosmic address question, and I clicked the wrong button. So our cosmic address gives a list in order of all of the places where we live, starting with Earth and going out. And so it goes from smallest to biggest. So we go from Earth to the solar system. The next is the Milky Way galaxy, followed by the local group. So you want to know those in order from there, okay? The distance, 6 trillion miles that light travels in 1 year. This is a definition question. So what is that the definition of? That's the definition of a light year. Remember that light year is, oh, I have a chat. All right, good. Light year is a distance. Sorry, I'm a little distracted this afternoon. There's a lot to look at when you're doing these on Zoom. Okay. While the sun is only 8 light minutes away, the next closest one of these is 4 light years away. So this is when we were talking about the scale. We were thinking about how far away things are, and the sun is only light minutes away. But what is an object that's light years away? So that's what I'm asking here to sort of translate this question. What is something that is light years away? It's not the other planets in our solar system. They're light minutes away. It's stars, okay? So stars are light years away. Planets are light minutes if they're close, light hours if they're farther away, like Neptune is light hours away. Stars are light years away. The Milky Way galaxy, 100,000 light years across. So just have a sense of that scale, and that'll help you too with that cosmic address. Solar system is light hours across. Then you get to stars, right? That's kind of the next thing in the Milky Way galaxy, and that's light years. Okay. All right. Let me know. I'll try to pause, take a breath every once in a while. Let me know if you have questions. Okay, we're going to move on to the scientific method. What is a generally accepted idea in science that tests have so far failed to disprove? This is another definition, so you need to know the definition of a theory. Important parts here, it's generally accepted. It has been tested. Well tested is another way to think of a theory. And how do we test theories and hypotheses? We try to disprove them. So just to highlight some of those terms and things that we talked about there. A very well-tested scientific idea that are of fundamental importance. So this isn't a theory. The last one was a theory. It's a next step up, which is a law, a scientific law. It's not only gone some tests, it's gone many, many, many tests, and it's fundamentally important. We'll talk about Newton's laws later in the semester. When a scientist tries a series of different tests that attack his hypothesis from different directions, he's trying to what his hypothesis to see if it stands up to scrutiny. So we're getting all the different parts of the scientific method here. This is what I was trying to emphasize before, which is disprove. In science, we don't prove things. Instead, we try to attack them. We try to disprove them. So we run tests. You might have said he's trying to test his hypothesis, but to be more specific, we want those tests to attack it, to see if the hypothesis will fail. If the hypothesis doesn't fail, then it might move to the next step of a theory. Okay. The generally accepted idea that the universe is the same everywhere on large scales. So we've moved from the scientific theory to this other idea. This is the definition of the cosmological principle. So I want you to know what the cosmological principle is, right? I just read the definition there. But I also want you to know, have a sense of what it means. What does it mean that the universe is sort of the same on large scales? Okay, so according to the cosmological principle, these are the same on Earth as everywhere else in the universe. Okay, this is one of the things that the cosmological principle means or implies. And the answer is physics, right? The physical laws, the laws of nature obeyed by matter and energy. Hopefully, the cosmological principle says, we're assuming that physics stays the same, that the physical laws are the same here as everywhere else. That way, we can begin to study things that are far away, right? That is another Let me go back to this review sheet. That is another implication of the cosmological principle. So the implications are that we are not unique. We're not in a special place in the universe, that the laws of physics are the same everywhere. And so that means that we can study close by things to learn about things that are far away. Okay, so go back to your notes, that's all in there too. So far we have covered this first section under what is astronomy, defining most of these terms, answering these questions. I think we didn't really specifically talk about the speed of light, right? So with the speed of light, what I want you to know is that it is a finite speed. Light doesn't travel instantly. It travels very fast, but not instantly. And that is a speed, whereas a light year is a distance. So keep those two things in mind. Okay. I'll take another breath in case anybody has questions here. Okay. So now we're going to get into the fun stuff, maybe also tricky stuff. We'll see. We have the celestial sphere. So some basics about it. What direction does it rotate? So now you have to think, well, which way does the Earth rotate? And then the celestial sphere rotates the way that we see the stars move. So east to west. Sun rises in the east, sets in the west. That's the same way the stars rotate, the moon, the planets, they all look like they go from east to west. But that is because the Earth is going in the opposite direction, west to east. Okay, so begin to get that mental picture of rotation. So how long does it take? That's what I mean by length, for the celestial sphere to rotate once. One rotation of the celestial sphere. We imagine that it rotates. It rotates at the same rate as Earth rotates, right? One day or every 24 hours. Okay. The celestial poles and the celestial equators are projections or extensions of these. Right, so the celestial sphere is this map, and we are imagining ourselves, Earth at the center, and we project Earth out. Earth's north and south poles project to the celestial poles, and Earth's equator projects out to the celestial equator. And the rotation is the same amount of time, the same 24-hour rotation. The reason the ecliptic is tilted 23.5 degrees to the celestial equator, right? This is because not anything having to do with our map, but it's because of the Earth. We always want to bring our celestial sphere map, that imaginary map, back to what's actually happening on Earth. Somebody didn't just decide there was this tilt. It's because the Earth is tilted, right? So what do we call the constellations that are on the ecliptic? They have a special name because they are the path of the sun. I'm always pushing the wrong button. The zodiac. So that's the definition of the zodiac. They're those constellations that are specifically on the ecliptic. You don't need to know the names of them, but be familiar with some of the pictures, like from our lecture tutorial on the ecliptic. Just to have a sense of which way they go. So if you see those same pictures or pictures that are like that, figures that show certain constellations, you'll remember how they move, right? How does the sun go? How do the constellations on the ecliptic go? Just like we did in the lecture tutorial, right? Don't forget to study those lecture tutorials. I can't really give you the same depth of question on the Jeopardy that I can give you on a lecture tutorial, but you will see some of those questions on the test. So review those for sure. So this category, seeing stars, imagines that we're at different places on Earth, and what will we see, and how are things arranged. So just starting out with groups of stars that are used by astronomers to separate the sky into 88 regions. We've already used this word. This is just the definition of a constellation, right? This is how astronomers use constellations. They're fun just to look at in the night sky, but they're useful as well to map things out. Okay. When all the visible stars are above the horizon for the entire night, none of them rise or set, such as when you are at the North Pole. What do we call this? These are the kind of stars that never rise or set. They are circumpolar stars. Stars that circle the pole, they never rise or set. So that's just the definition, but then you need to know, where do you see circumpolar stars? Okay, so then we'll get into that with these next questions. The place on Earth where all stars on the celestial sphere are visible over the course of a year. So, as a hint, this is also the place where you don't have any circumpolar stars. You get to see all the stars if you keep watching, if you have clear nights. It's on the equator. All the stars rise and set. The celestial poles are on the equator, and you have no circumpolar stars. Okay, and you get to see them all. Latitudes on Earth where you can see stars rise and set and circumpolar stars in the same night. Hint here is that it's most of Earth, including us in South Louisiana, the mid-latitudes. So we divided the Earth into sort of three places: the equator, the mid-latitudes, and the poles. When I ask you on the review sheet to know what stars you can see there, I'm not talking about names of constellations or names of stars. I'm talking about, do you see circumpolar stars? Do you see stars rise and set? Do you see the north hemisphere of the celestial sphere? Those kind of questions. Okay. Ancient sailors knew that this was equal to the altitude of the North Star in the night sky. So they look up at the night sky and they measure how high up is that North Star, and that tells them where they are on the globe, specifically the latitude on Earth. So remember, latitude, those are the lines that go horizontally across the globe, so they look like a ladder, right? That tells us, are we closer to the equator or closer to the pole? Equator at 0, pole at 90. Okay, so I want to look back. No comments or anything? Okay, I want to look back at the review sheet because I wasn't able to cover everything. We still have a few more parts. I want to talk more about the ecliptic, but didn't cover everything as far as what stars you would see. We didn't talk about the poles. We talked about the equator. You see all of the stars, and all of the stars rise and set. And mid-latitudes, you get a mix. But if you're at the poles, you only see circumpolar stars, okay? The stars just look like they're going around and around. At the North Pole, you see the North Star and the stars that go around it. At the South Pole, you don't have a South Star, but you see the circumpolar stars there as well. And you only see half of the hemisphere. You only see at the North Pole, the northern hemisphere of the celestial sphere, or at the South Pole, the other half. Okay. Mid-latitudes, again, that's a mix. So I wanted to make sure to cover that on the poles. Otherwise here, we defined most of those things. We'll come back to some of these. We haven't finished all these questions yet, okay? I know this is fast, but this is sort of meant to be a quick review. And if I go fast, we do it in less than an hour. But you can always go back and think about these things. Send me an email if you have a question, if something I said didn't make sense. Okay. So the sun and the ecliptic. This is again getting back to that lecture tutorial on the ecliptic. The reason the sun is not always in the same constellation as seen from Earth. So when we say the sun is in a constellation, we're imagining those zodiac constellations behind the sun during the day. We can't see them, but we imagine that they're there. But they're not always in the same one, and that is because the Earth goes around the sun. So the Earth's position changes relative to the sun, so it changes relative to the stars as well. So the sun looks like it's in a different constellation as we go through the year or as we orbit. And we call this yearly path of the sun as seen from Earth. It goes through the zodiac constellations, but more specifically, we call that the ecliptic. Right? That's one way to define the ecliptic. We define the ecliptic in several different ways. One is the yearly path of the sun. Two is it's the plane of the solar system. And three, it's the zodiac constellations, right? Okay. The time it takes for the sun to make its way through all of the zodiac constellations, or a full trip around the ecliptic, or a full trip of the Earth around the sun, which is 1 year. Again, we have to translate from that Earth-centered view to the sun-centered view. And remember, it's the Earth that's moving, not the sun. If you observe the sun for 2 days in a row, it will be in front of the same or a different constellation on the second day. This was at the beginning of that lecture tutorial. We had a picture and we said like December 1st, it's here. And where is it? Like December 2nd. Well, we talked about it in different ways. We said at noon, at 3 p.m., December 1st, December 2nd, and then January 1st. So remember those. Go back to those pictures, look at them, think about them, because you'll find that over the course of a day, the sun is not going to move very much. It's going to be in approximately the same position or in the same constellation. So if the question asks a few hours later or a day later, you're going to be in the same constellation. However, if you're talking a month or 6 months later, you're going to move to a different constellation because it's dependent on the Earth going around the sun, which takes a year. Okay. When the sun is in the constellation Cancer, this is the time we can see the stars in Cancer. Is that true or is that false? Right? What are we saying with that statement? Remember what we said about what it means for the constellation to be in Cancer. This is a false statement. We can never see, I know it's worded weird, sorry, but we can never see the stars in Cancer, the actual constellation, if the sun is in Cancer. If the sun is in Cancer, it means Cancer is up during the day behind the sun compared to us. Okay? So that's just another question, making sure you have this mental picture of the celestial sphere and the motions of the stars and the sun and all of that stuff. Okay, so if it helps you, make a model, right? Use your hands, draw a picture. By the way, you can draw on the test. If it helps you to draw things before you answer a question, do it. That is totally okay. Go back to the pictures that you saw in the lecture tutorial. You will see a couple of pictures that are similar to the lecture tutorials. So go back and review that. So that last section, we kind of did these questions here. Yeah, so we said it doesn't change constellations in a day, the sun, but over a month, it will be in the next constellation around the zodiac, and it takes a year to get through the whole zodiac. Okay. We didn't cover astronomical units. That might be in this next section. Might just have that in the wrong place. Oh, sorry, wrong thing. No. I just want you to go away. Okay. All right, sorry about that, guys. Am I still sharing my screen, or did I accidentally? Anybody? Okay.
No,
I think,
you're not sharing your screen.
okay, that's what I thought. I think I accidentally messed that up. So here we go, back now. Thank you. We're almost done here, y'all. Thanks for hanging in there with me. So we are going to be moving to kind of the next topics, trying to match up the celestial sphere with the seasons. And so this transition is thinking about how the Earth orbits and the tilt of its axis. Okay. And so here's that definition that I was just talking about. The definition of astronomical unit is the distance between the sun and the Earth. So we learned when we talked about the seasons that this distance isn't the same all year round. It changes very slightly, not much, remember, because it doesn't make a difference in the seasons. So this astronomical unit is just taken as an average, but it's a distance unit. It's a way that we can measure distances to planets in particular within our solar system. Okay, so that's the definition. Name of the place where all planets orbit the sun. And so this is, again, getting our mental picture of the ecliptic matched up with Earth going around the sun. So that's just another definition of ecliptic. The reason the sun is not directly over the equator for the whole year. Right? If the sun were directly over the equator for the whole year, we would not have seasons because there is a tilt, right? The Earth's axis is tilted by 23.5 degrees. So the sun on the ecliptic is not matched up with the equator. The ecliptic and equator are also separated by that same tilt of 23.5 degrees. Cause of the sun appearing to move on the ecliptic over the year. We've already talked about this a couple of times, but it's because the Earth is moving, right? The sun looks like it moves because the Earth is moving, and the sun is on the ecliptic. So we got to keep that ecliptic equator straight and kind of remember all of our motions. So that was just to kind of connect the ideas about the celestial sphere with the seasons. Okay, so that just finished up that section. Why don't we always see the same stars? And our last section here is on the seasons. It's hotter in the summer because we get, and really there are two answers here, right? Because we said there are two main reasons for the seasons, but I was looking particularly for more direct sunlight. You could have also said, instead of more direct, you could have said more hours of sunlight. Good, you guys got that in the chat, okay? So it's hotter in the summer because we get more direct and more hours of sunlight. I'm sure that'll come up again in other questions, but all right, escape. The reason the sun in the sky is in the sky longer in the summer. Okay, think about your mental picture of the celestial sphere again and realize that because of the tilt, and I wish I had written this in this question, or in the question, the answer, the Earth's tilt puts that ecliptic higher in the sky in the summer. So the sun has a longer path. It goes up higher. It's higher at noon. It's further north in the sky. So it takes longer from rising to setting, and it's all because of the tilt. This would be one direct result of the Earth having no tilt. Okay, so take that Earth in your head and put it straight up and down and think about the sun shining on it. And you would see that we would have no seasons because you would get the same amount of sunlight at the same amount of directness all year round. It would be like living on the equator. Same sunset, sunrise times every day, and same intensity of light. Okay, the day on which the sun is the highest it will ever be in the sky in the northern hemisphere. Okay, so I was just talking about this in that other question. We said it was summer, right? So what particular day in the summer? It's the summer solstice, which comes around June 21st approximately. The sun is the farthest north. The winter solstice is the opposite. So remember, when you're thinking about the definition of solstices, that these are not just the longest and shortest days of the year, but they also tell us something about where the sun is. Summer, the sun is furthest north, and it's got this long path high in the sky on the ecliptic. Winter, the sun is low in the south with a short path, short day. Okay, check the chat here. Good. Okay. Escape. Last question here. The day when the sun is at the point where the celestial equator crosses the ecliptic. We just said that the equator and the ecliptic, not the same. Hopefully you got that by now, but they do cross, and those are the equinoxes. The fall or autumnal equinox and the spring or vernal equinox. So recognize what those words mean. The equinoxes also give us equal hours of light and dark. So it's equal, and it's where it crosses. Think about that X in equinox is where the equator crosses the ecliptic. Okay, so that is the end of our Jeopardies. We just spent a long time on the seasons lecture tutorial, so look back at that, make sure you got all the answers, look in that Google Slides to make sure you've covered all of that, because you might see questions like that as well. So we have seasons, again, to review, because the Earth is tilted, and that gives us a change in the directness of light, and it also gives us a different amount of light, right? We talked about where the sun is in the sky on the solstices. The sun is on the celestial equator on the equinoxes. And then go and look at that lecture tutorial, look at the figures. Make sure that you can identify, oh, this is spring in the southern hemisphere, or this is, or not spring, sorry, summer in the southern hemisphere, or winter in the northern hemisphere, or whatever. And then that last question, what if we change the tilt of Earth? We had in Jeopardy, what if there was no tilt? We had no seasons. But we also talked about in class, what if we had a big tilt, right? What if the Arctic Circle was facing the sun? Then we would have really different seasons. The Arctic Circle would be warmer than Florida. So think about that mental model in your head as well. Now I really am gonna stop sharing. Last just moment here, if anybody has a question, wants to chime in, anything. That went pretty fast, faster than when I do it in person. Okay, yes, the test is multiple choice. It has 34, sorry, I just finished running copies today, 34 multiple choice questions. So you have the whole class period. Honestly, most people don't take the whole class period, but you have it if you need it. It is really plenty of time, I find, for students to take the test. Write on the test. You will get the test papers back if you want them back. So if you want to make notes to yourself, that's totally okay. You don't need a Scantron. I have a form. I'll show you this form at the beginning of class, but it looks like a Scantron, but it's not. You just need a pencil. So that saves you the effort of getting a Scantron, and it's a little easier for me to grade. So Did I get all those? Anybody else? Oh, best study tool. This review sheet, make sure that you can answer the questions in your own words. And when I say answer the questions, not just the short one-word answer, but actually be able to explain. The lecture tutorials, don't forget about those. For these topics, the ecliptic and the seasons, those are really, really helpful tools as well. Generally, I just kind of tell people to not just memorize your notes, but really to try to understand. This is really important for this section, understanding that model of the celestial sphere. Get something, pick up, look, I have an apple on my desk, pretend that it's Earth, give it a tilt, think about where the equator is and the axes are. Think about how that celestial sphere would move or how it would move around the sun. Those things can really help you mentally grasp it. And then if you have a good mental model, it's going to be easier to answer the questions. But I usually tell people to go to that review sheet. Also, don't forget there is the old test from last year posted on Moodle. Take that, see how you do. If you miss a bunch from one section, then you know that that's what you really need to study. So anything else? I'm trying to think of anything else. I don't know. No more questions? That's good. Okay. You can always email me. I'm going to post all this stuff right now. You can email me if you have questions. I don't stay up late, but I do get in pretty early in the morning. So if you have questions, let me know about that too. Oh, how similar is it going to be to the old test? Very similar. You won't see the exact same questions, but the style is the same. I don't change my style. I write new questions. Occasionally I use old questions and change them around a little bit. So that's a lot what you would expect. The other thing about the old test, if you scroll down to the very end and it has the answers, and then it has a keyword like, is it remembering or understanding or applying? That kind of tells you a sense of the level of the question. If it's remembering, it's something that's basically straight out of the notes. It's a memorization kind of thing. If it is understanding or applying, you're getting into more of the lecture tutorial type of question where you have to understand the whole model to be able to answer the question. So if it helps you to kind of look at that and see how I try to put a good mix of memorization and the sort of more challenging critical thinking lecture tutorial type questions on there as well. Every once in a while I do reuse a question, and every once in a while I use a clicker question too. So the old clicker question, or all the clicker questions, are posted on Moodle too, so you can review those as well. Every once in a while I'll stick one of those on the test. Not always, but sometimes. Okay, anybody else? Give it one more second here. Okay. Okay, so we'll call that a day. You can email me any other questions, and I will see you tomorrow. Just bring a pencil. You can sit where you normally sit. I'm not going to do a seating chart for the big classroom. So just have a seat and you'll get your test. Let me know if you need anything. All right, have a good night. See y'all. Bye.